All right, so I thought I'd take the break and then come back at graphing the logarithm function. So and we're not just graphing it, but questions about the graph. All right, so what we have is a function like this, and it they're going to ask us to find the domain, which would just be found by x plus 1 is greater than 0 and solving that. But that's going to help us with the graph because we know that by now we should know what to do when a minus sign is thrown into a graph, when a 1 is thrown into that position, and everything else from the image. So well, let's break this down. So I would start with the graph. I know the author is not going to do this, but I would start with the graph y equals minus ln x. In other words, I like to just get rid of the numbers, but not the minus sign. Learn how to graph that. And then this new graph, y equals minus ln x plus 1, is going to be this graph shifted over 1. All right, what does the minus do? Well, we'll see. All right. So here's the other started even earlier, y equals ln x, y equals log base e of x. This is a graph you should know. What happens if we insert the minus sign? It reflects the graph in the x-axis. So it reflects the graph in the x-axis, so it's like flipping it like a pancake through the x-axis. And then what happens when I add the 1 to the x? Shifts the graph to the left by 1. Not just the graph, but the asymptote. Every point gets shifted, and even the asymptote gets shifted. So then they ask us what's the domain and range of this. Or maybe they asked us before, but the domain was x is greater than -1, and the range is -infinity to infinity because it uses all the y values. So we have a pretty good presentation there. All right. Anyhow, they're asking us now to find the inverse. So remember how to find the inverse. It changes to y, but I'm going to change y to x, and I'm going to change x to y and solve that. So solving that, remember again, this is log base e, so the base gets reunited with the exponent, and you can see the inverse function. Then you do all of the properties that we did in the previous section. Graphing a function and its inverse. All right, so that's basically what they did here. If you graph a function and its inverse, pretty noisy little function here, but basically if you took any one of these points, A, there'd be an inverse point on the green graph, A inverse. And it's like taking the original graph and flipping it like a pancake in the line y equals x. So I'm not really a fan of this particular one because it's not really obvious that that's what you get. When you flip one graph, you superimpose it on the other one. But I do like this process for, one of the graphs we had earlier. If you have y equals e to the x, and y equals ln x, the symmetry is very clear with respect to this line y equals x because these are inverse functions. There it is. Okay, that's not the actual one I was just talking about, but this one is log base 10. That's this one. And if I thought of it as y equals 10 to the x, that would be this one. Their inverse is, and they have that kind of obvious relationship where if I flipped it like a pancake through this line, they would superimpose on each other. the interesting thing about this whole process that the author is kind of not talking about is the other saying we're graphing a logarithm function and its inverse. And what the author's really trying to say is we can graph a logarithmic function using its inverse. Or not. You don't have to do that, but they're going to, that's kind of what they're getting at, I think. Hard to tell what they're getting at with all of these, all of this. You know, here's the logarithm function of log y equals log x. If you subtract 2 that, from the x, that's a shift. Shift 2 to the right, horizontal shift. If you multiply it by 2, it stretches that previous graph along the y-axis. Well, I guess we're done. Yeah, that was the graph right there. Okay. So hopefully everything makes sense. In other words, why is it x equals 2? Because it had been x equals 0, but I shifted it. You know, why is this? You know, at 12 it went up 1, and now at 12 it goes up 2 because I stretched it. What are they asking here? Find the range. Well, the range, the domain and range. Of this. No, they're finding the inverse. Okay, I see. So now to find the inverse, set it equal to y, switch y and x, and solve it. Might take a little bit of time to figure this out because there's invisible things like the base 10, but it's 10 to the 2/3 to the x over 2. Anyhow. Process will give us that. I don't really have anything to add to this. It's just moving the, you know, solving the, well, solving for y in this procedure, which is what we typically do. And how did we get there? By scrambling and rewriting the logarithm into exponential notation. Then we have a couple of examples of it, or an illustration of the two, and they should, you know, reflect through that line there. I think I will say something about graphing logarithm functions that the authors seem to miss, but let's go ahead and stay with the outline. I'll come back to that in this video. All right, so solving a logarithm equation like this, when there's only one logarithm, does involve scrambling. And if you remember the scramble, it's going to be 3x minus 4 equals 5 raised to the 3. Remember, this is the exponent that I put on that base. So I reunite the base with its exponent. 3x minus 4 equals 125. What am I going to add 5? 3x equals 129. X equals 129 over 3. That actually works. What is it? 43. All right. Could have used my calculator, but you know, dividing this, you get 43. All right. So this one, notice where the x is. That's a little unusual, but I mean, usually x is part of the argument, but on this one, I'm still going to scramble it. 81 equals the base and square it. We know the solution to this. Let me write it this way. X squared equals 81. We get x equals, you know it, plus or minus 9. But hold on. There are restrictions. You don't really talk about the restriction on the base very often. It doesn't have a name. It's not like the domain problems we had before. But the base can't be negative and it can't be 1. So I do have to exclude the negative number, not because of the domain again, just because of separate rule for a, the base. All right, so we get that x should equal 9, solving those equations. 43 and plus or minus 9, they got rid of it. All right. Using a calculator, but I want to seriously talk about graphing because there's a few, I know, gimmicks out there, and I know what's going on. Some students fall for these gimmicks, and that's fine. I just want you to know what's there. So let's do a straightforward, probably easiest graph we could do. If I say graph y equals log base 2 of x. All right, and why are there gimmicks out there? Well, because of something you haven't really encountered for a while. It's this idea that you have to pick your x values. You have to pick x values that make sense. And that's usually really easy to pick your x values, but not with logarithms. And when I say it's something you haven't struggled with for a while, there's another function where picking your x values is a little bit of work, and that's square root of x. But, you know, you struggled with this in 4th grade, but it's been a while. But what I mean by that is, you know that -1 doesn't work. I pick 0, and that's the square root of 0, right? I pick 1, and it looks like it's easy, but I don't pick 2, and I don't pick 3. I got to pick 4, because I know how square root works. 4, square root of 4 is 2. I pick 9. Square root of 9 is 3. So you see how I'm not just picking numbers at random here. I'm picking numbers because I know they're going to work. Let's get rid of that memory from elementary school. And how does that apply here? Well, I certainly don't pick -1 because that doesn't work. I can't even pick 0 for logarithms. That doesn't work. Would just give me an error on my calculator. You know, what numbers should I be picking? Well, I should pick numbers like 1/2 and 1 and 2 and 4 and 8. These are numbers that give nice answers. And I know that because I know logarithm well enough, hopefully, at this point. What if I did put an 8 in there? What exponent would I put on 2 to get 8? Yeah, the answer is 3. What if I put a 4 in there? What exponent would I put on 2 to get 4? 2, 1, 0. How about this one? Why did I put 1/2? Log base 2 of 1/2 is -1. Why? Because the exponent I put on 2 to get 1/2 is -1. So if these are my points, A, B, C, D, E, what would my graph look like? Well, at 1/2, it's -1. At 1, it is 0. At 2, it's 1. 1, 2, 3, 4. At 4, it's 2. And at 8, it's 3. And hopefully you remember the shape of this graph. And to me, this would be the most direct way to graph, if you remember the graph I was doing, y equals log base 2 of x. That's the graph. What I was saying is, if you're going to look at this somewhere online, maybe you probably won't ever see another human being do what I just did, which is directly graph logarithm. Almost everybody thinks they have a gimmick, and they think their gimmick is a good idea. Let's go over a gimmick. All right. So here's my gimmick. I want to populate this table. It's not my gimmick. It's a very common gimmick, though. I want to populate this table for that same graph I just did. Log base 2 of x. But for some reason, I'm scared. I don't want to pick numbers like 8 and calculate the exponent. I'd have to put on 2 to get 8. So how do I fill in a table without doing that? Well, as it turns out, I can fill in a table by hold on. Using this gimmick. Oh, it's supposed to be x. All right, just so you know what I'm trying to do. I'm too afraid to fill this in. All right. So what can I do? Well, you know what? Y equals 2 to the x is related to y equals log base 2 of x. And the amazing thing about this is it's really easy to pick my x values. -1, 0, 1, 2, 3. Very easy to pick values for this one because I can put anything in for x. Now, you might not see it yet, but there's a connection that I'm going to make between these two tables. But for this table, it was really easy. This is 2 to the -1. Well, that's 1/2. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 8. What is the connection between this table and this table? They're inverses. If your tables are inverses, it means I can change the x and the y. So 3, 8 becomes 8, 3. 2, 4 becomes 4, 2. 1, 2 becomes 2, 1. 0, 1, 1, 0. And even this one, 1/2, -1. This is the exact same table I had on the previous page, except I earned this table by understanding logarithms. This time, I kind of used a trick to get this table, a bridge of some kind, where I took a function that I learned last section and said, you know what, if this is the inverse, I can flip it, switch the x and y, and I'll get my points. So last time I was calling something like this A, and this would be A inverse. As long as I know that this function has an inverse, and this is the inverse, I suppose this works. Then what? Well, I don't really have much more to say about it. Then you'd plot those points, and you'd get this very same graph, but it is a way of easing into it. So I have this theory on this, and it is when you watch, I don't know, YouTube videos or read a book or really anything, those people feel like they're adding value by giving you some indirect route to the answer. Because who wants to watch a video that says, you know what, you should just understand logarithms well enough to know that 8 works in this particular equation. 4 works in this equation. 2 works. I didn't put in 3 because log base 2 of 3 doesn't really have a nice answer to it. You can learn what logarithm means, or you can use kind of a bridging approach to get there. But either way, be able to get the points and get the function, and just be familiar with this function, with this graph. All right, that's logarithms, and there's more to logarithms. The rest of the chapter is still logarithms as well. So there's more to it than that. But this was just kind of the introductory part of logarithms where we are graphing logarithms and working with logarithms. All right. That's 6.4.